let's introduce some terms in chemistry that are commonly employed when chemists discuss the subatomic particles that make up all atoms. Now remember, there are three subatomic particles we're going to concern ourselves with. Those are protons, neutrons, and electrons. And all atoms are built from these same three subatomic particles. It's just a matter of how many of the subatomic particles are present to determine which and what type of isotope of an element you might be dealing with. So we're going to begin by introducing the term the atomic number. And as it says here, the atomic number counts the number of protons in the nucleus of an atom. It turns out that the atomic number, counting the number of protons in the nucleus of an atom, dictates what type of atom and what element that atom belongs to. All atoms of the same element must possess the same atomic number. All atoms of the same element have the same number of protons. For instance, if you look at the box of the element in a periodic table, prominent in that box is the chemical symbol, which we talked about for some length last period. At the top of the box is a numbering, and it seems at the top of each box it's a sequential numbering. And the modern tables go now, this is a little bit dated what I'm showing here, modern tables go up to element 114. And as they go to element 114, what you'll see is that it's sequential, starting at number 1 and going up to 114. Well, not only is that number at the top of the box sequentially counting the number of elements that exist, it is also telling you the information of the atomic number. So each box has a unique number, each box has a unique symbol, and that number at the top of the box above the symbol is telling you the atomic number, or the number of protons in that particular nucleus. So vanadium is in box 23. That means all vanadium atoms have 23 protons. Just any other one we want to pick, such as nitrogen, which is element 7. All nitrogen atoms possess 7 protons in their nucleus. The second term we're going to introduce, which describes the subatomic particles in an atom, is known as the mass number. Now, the mass number deals with the total number of particles present in the nucleus. And remember, the subatomic particles present in the nucleus are the protons and neutrons. Sometimes these are called the nucleons because those are the two of the subatomic particles that you find in the nucleus. So what is the mass number then? The mass number is the number of protons and neutrons present in a nucleus. Now, the reasoning behind the name is probably due to what we had seen near the end of the lecture last time when we looked at slides showing the mass of the subatomic particles. The proton and neutron are very similar in mass, differing only at the 4th significant digit, and the proton and neutron are some 1,800 times heavier than the mass of the electron. So essentially, when you start to pile up a multi-proton and electron and neutron atom, the vast majority, the vast percentage of the mass is due to the nucleons. The vast percentage of the mass present in an atom is due to the protons and neutrons. So this mass number counts the total number of protons and neutrons that are present in atoms. Now, as for general trends, the so-called lighter elements, those present in the first 3 rows, we'll say, roughly, maybe even going on 4 rows, they generally have a 1-to-1 ratio of neutrons and protons in their nucleus. When you get to heavier atoms, they generally have a 1.5-to-1 ratio of neutrons to protons. So the lighter the lighter atoms with fewer protons in the nucleus, you only need essentially one neutron per proton to hold it together. But as you get to further down the periodic table, rows 5, 6, 7, by the time you get near the end around lead, now by that time there's so much positive charge present in the nucleus, you need a higher ratio of neutrons to help hold that together. So by that time, you've got about 1.5 neutrons per proton holding these nuclei together. Now, once you get to a multi-proton situation, or anything above 1 proton, it is necessitated that neutrons are present to hold the nucleus together. You can't bind 2 protons into a nucleus without the presence of neutrons to help hold that nucleus together. And it's very strange in the sense that the neutrons and protons can come in slightly different ratios in a stable nucleus or an unstable nucleus. If the ratio of protons to neutrons is not correct, then the nucleus is unstable and spontaneously adjusts by changing the number of nucleons to get to a stable nucleus. Now, I will say it again, that is spontaneous. We can't stop it. When the nucleus is not in a proper ratio, it undergoes its own internal transmutation of change of, in some instances, the number of neutrons, and in some instances, the number of protons. Both processes occur. Sometimes it's both transmutating at the same time. And the effect of this is to take the nucleus to a stable ratio of nucleons. Now, this nuclei, not all nuclei do this. As a matter of fact, the vast majority of nuclei are stable. But the ones that do undergo these kinds of processes are the familiarly called radioactive isotopes of particular elements. They don't like the ratio of their protons to neutrons, so they make adjustments spontaneously. And again, these are things we can't stop, no matter if we change the temperature, douse them, remove the air from them, remove light from them. It doesn't matter, they will still undergo these spontaneous processes to adjust their nucleons. So, with that in mind, we will state that there are isotopes of an element that can be different atoms that are residing in the same type of element. And first of all, note that if you are an atom of an element, you must have the same number of protons. All atoms of oxygen have 8 protons. All atoms of lithium have 3 protons. So once you change the number of protons, you've changed the atom to another element type. But the atoms don't have to have the same number of neutrons. Now they're close, but they don't have to be exactly the same number of neutrons. So when you have an isotope, they have certainly, if they're isotopes of the same element, they have the same number of protons in them, but they differ in the number of neutrons. Now, another way we can say that is that isotopes have the same atomic number, but they have different mass numbers. Remember, the mass number counts the number of protons and neutrons. The atomic number only counts the number of protons. Okay, before we introduce a representation for the subatomic particles that are the electrons, let's introduce the idea of the charge on atoms and the so-called things known as ions. So if you have a neutral atom, neutral atoms have net zero charge, and they have equal numbers of the positive units and the negative units of charge. So of course, neutral atoms have equal numbers of protons and electrons. Now, if you have a so-called anion, an anion is a negatively charged atom. And of course, it seems obvious that to make an atom negatively charged, somehow it has more of the things carrying negative charge than positive charge. It has more electrons than it has protons. So to form an anion, you have it gain protons. Form an anion, you have it gain electrons. Now, when something gains electrons, simultaneously, something else somewhere in the universe had to give that electron to that material. And when something gives up some of its negative charge, it is becoming a cation. So what we will say is that cations, not cations, cations are net positively charged atoms, and they become net positively charged not by gaining protons. They get net negatively or positively charged by losing electrons. Now the idea here is that it is much, much, much easier for an atom to lose an electron to become positively charged than it is for it to gain a proton to become positively charged. Energetically speaking, the action of gaining a proton, though possible, first of all, would change the element into a new element because you now have a different atomic number, so you're literally a different element than you were before. But more importantly, that it is so energetically difficult for that to occur that under all processes we will deal with, and certainly under all chemical processes, when something becomes positively charged, it does so by removing electrons. As a matter of fact, when you walk in your bare socks across a carpet, you're originally neutral, the carpet's originally neutral. You gain a huge amount of negative charge by rubbing electrons loose from the carpet fibers. You become net negative, the carpet becomes net positive when you do such a thing. So let's look at a symbol of an element, and let's look at it dressed up with some numbers that will show you the number of subatomic particles that it possesses as well. So what I have here is the example of the atomic symbol for Zn, and it has a left superscript of 65. Now, from this information, it's possible to determine the number of subatomic particles present in this particular isotope of zinc. The subscripts and superscripts are the positions where these numbers are given. So, first of all, let me turn to the left subscript where there is nothing present. And if there is nothing present, the reason there is nothing present there is that this is kind of redundant information. If there is a value there, it has to be 30. Why? Because the left subscript is the atomic number. But zinc, all zincs have 30 protons, so the number that is there must be 30. If the number there is not 30, it is not a valid representation for this particular isotope. So really, a lot of times there is no left subscript given because just from the symbol of the element, you should know how many protons are present. So if there was a number there, it would have to be the number 30. If there isn't a number there, what I would do is go to the periodic table, look for the box Zn, and look at what number is at the top of the box, and that number is the atomic number. So we now have determined that this has 30 protons in its nucleus because it's a zinc. Now I'm going to turn to the right superscript. Again, there's nothing listed. And if there's nothing listed, we can only assume that this is a net non-charged atom. If there is a number there, it'll either be a positive or a negative number telling me if there's a net positive charge or a net negative charge. So in this case, there is no number given. I can only assume, therefore, that it is neutral. If it is neutral and we know that zinc has 30 protons, then it must have 30 balancing negative charges. So this isotope must have 30 electrons. So it is a neutral atom with 30 electrons to balance the 30 protons. Then I will turn to the left superscript. The left superscript gives the mass number. The mass number counts the number of protons and neutrons present in the nucleus. The mass number here is given as 65. And because this is element zinc, which has 30 protons, therefore, if I subtract the mass number from the atomic number, I will get the number of neutrons, and I would find this has 35 neutrons. Another example of finding the subatomic particles in a representation of an atom. Here I see the element with the symbol O. O, of course, stands for oxygen. So because there's no left subscript, I have to tell how many protons it has based on its symbol. I look on the periodic table and I notice O is in box 8, which tells me that this has atomic number 8, or 8 protons in its nucleus. I will then turn to the left superscript, which is its mass number. Mass number is 16. That means it has 16 protons plus neutrons. And since it has 8 protons, it must therefore have 8 neutrons in this particular isotope. But now, as was not the case last time, there is a right superscript. And the right superscript is -2. And remember, as we talked about in the last lecture, each unit of charge tells you the number imbalance of the protons to neutrons. Since this right superscript is -2, that means there are an excess of 2 negative charge particles in the isotope. So there are 2 extra electrons compared to the number of protons. So since this particular isotope has 8 protons, it must therefore have 10 electrons in order to have a -2 net charge. Some more examples of this concept. Let's look at the top left one, which shows the symbol Ca, which is the element calcium. I turn to the periodic table. There's no left subscript. If there was a left subscript, it would have to be a 20. Why? Because all calcium atoms have 20 protons. They all have atomic number 20, because this is element in box 20. Then I will turn to the left superscript, which is the number 40. That is the mass number, since it has 20 protons in the nucleus and has 40 nucleons total. It must have 20 neutrons in that particular isotope. Now, let's look at the right superscript, which is a +1, which indicates this is a net positively charged isotope. Now, maybe your inclination would be to say, well, if it's +1, then maybe it shouldn't have 20 protons. Maybe it should have 21 protons. That's not the way you should think of this. All isotopes of calcium must have 20 protons. If they don't, they are not calcium. They're actually the next element over, which I believe is germanium on the table. So that's not what this represents here at all. What the +1 represents is that it's deficient in electrons to make it positively charged. So if a neutral calcium, which possesses 20 protons, would have 20 electrons, since this is a +1 cation of calcium, it must have 19 protons. Likewise, we can do the other elements you see on this page. Zirconium, if I look in the periodic table, is in box 40, meaning it has 40 protons. it has a -3 charge, meaning it has an imbalance of extra electrons, so it must have 43 electrons. And because it has mass number 91, along with the 40 protons in the nucleus, it must have 51 neutrons. Then I show on the right, I show two so-called isotopes of hydrogen that are so familiar to chemists that they're given names other than the name hydrogen. The H with the mass number 2 is called deuterium. The H with the mass number 3 is called tritium. Turns out tritium is a radioactive isotope of hydrogen. Putting that number of neutrons in the nucleus imbalances it, makes it so unstable that it undergoes transmutation to try to become stable. But in any event, let's return to deuterium for a moment. Neither of these have a right superscript, so they are neutral in charge, and so the number of electrons equals the number of protons. All H's have one proton, no matter what isotope of H it is, so these neutral atoms have one electron as well. For deuterium, because the mass number is 2, it must have one neutron. So generally speaking, this is not what the majority of hydrogen isotopes are. The majority of them are H with the left superscript of 1, meaning they have no neutrons in their nucleus, only a single proton present. Now the bottom one, H3, the mass number being 3, all these H's still have one proton. Those must have 2 neutrons to go with the one proton in tritium. Here are 4 more isotope examples. I'm not going to go through the details of all these. You should be able to do these processes. You should verify the number of protons, neutrons, and electrons present in each case. Of course, at some point when we take an assessment on this, you will have the opportunity to demonstrate to me that you're capable of doing this. As we will look at in greater detail as we go along, we will find that the way electrons are arranged around the atoms of a nucleus ultimately dictates the chemistry that the atom undergoes. This is the first time I'm making this statement, but it certainly will not be the last. Chemistry is all about the electrons. It's about how the atoms enter into deals to change their current electronic structure or distribution of electrons around a nucleus. Most atoms are not satisfied with the way electrons are distributed, so they enter into changes which are accompanied by energetics, phase change, property changes, and this leads to the rich region of science that we call chemistry. So when chemists realized there was a subatomic structure to atoms, it was important that they could unravel how the electrons were distributed around the nucleus of the atom in order to help them understand the type of chemistry that the particular atom would undergo. So you can't just put on a magnifying glass on an atom to see the way the electrons are arranged. You can't even put it under the most powerful microscope that we possess to see the way the atoms are arranged, or the electrons are arranged around the atom, the nucleus of an atom. So ultimately, how the structure of the electrons around a nucleus was unraveled was to shine light on the atom. And the way that the atom interacted with the light allowed scientists to unravel the mystery of the structure of the electrons around the atom. So, as we say here, the probe that was used to determine the arrangement of electrons was so-called electromagnetic radiation. The reason we use that general term is that we generally equate electromagnetic radiation with the term light, but there are a large number of frequencies or wavelengths of light, of electromagnetic radiation that fall outside of the realm of what we typically mean when we say the word light. So electromagnetic radiation is a generalization of what light is, some of it not the kind of thing we can see, but yet it is still an important probe to unravel the structure of atoms and molecules for that matter. So what we will do now is spend a little bit of time discussing electromagnetic radiation. What it turns out to be is a propagating transverse wave that consists of a disturbance in space itself by changing space around us, by altering the electric field conditions of the space and the magnetic field conditions of the space. So as light propagates through space, it is constantly generating electric and magnetic fields. And as it generates these electric and magnetic fields, it enables the light to move through space. And we'll try to show a little bit about that on the next cartoon. This picture is attempting to represent an electromagnetic wave or light beam, if you like. Okay, so we show cartoons representing propagating electric and magnetic fields. You'll see, first of all, that this should technically be three-dimensional, so it's a little bit hard to represent. But having said that, let me try my best to say what's going on. I show a line along which there are up and down hills of red and blue. The up and down hills of blue are opposite signs of an electric field. The ones pointing upward, I'm going to say, represent a positive electric field, and the ones pointing downward represent a negative electric field for the blue part of what I'm showing. Now, what that means by the positive and negative lines up and down is that if you put a positive charge in there, it would get pushed upwards when the lines are going up, and a positive charge would get pushed downwards by the presence of this electric field in the region where the lines are pointing down. So electric fields change space around them, and they alter the space so that any charged particle in them experiences a force. So these lines are trying to show the direction of force that would occur if a charge is in the influence of this field. Now, perpendicular to the blue up and down lines, we see red right and left lines. Those are representing the magnetic behavior of the electromagnetic radiation. But now, instead of calling it positive and negative, as is done with charge, what we use are the connotations of interactions of magnets. We use north and south poles. So you would attract or repel a north or south pole in the way that the red section of the magnetic field is pushing or pulling other magnets. Now, the reason that electromagnetic radiation flies through space is that when you have a changing electric field, which we're indicating by the height of the lines growing and then diminishing and then falling to the opposite direction, growing and diminishing, changing electric field generates magnets. And likewise, changing magnetic field generates electric fields. So as electric fields change, they make magnetic fields. As magnetic fields change, they make electric fields. And this marriage of change between the two regenerates and moves the light through space. So believe me, it took humans thousands of years to understand this idea. Most of it was done by an individual by the name of James Clerk Maxwell. So we now are pretty satisfied with the picture of oscillating electric field generating magnetic field, oscillating magnetic field generating electric field. which allows the light to move through space. So the direction that the black line is pointing is the direction of propagation of the light beam as it swishes from positive to negative electric field and switching from north to south magnetic pole. We can reveal the wave character of light by looking at maybe just one of the fields without the little up and down lines. We'll just show the periodic, regularly repeating oscillation above a fixed starting point, above and below that starting point, which has the same reminiscent movement of the oscillation of the surface of water when you drop a rock in it. You undulate the surface to make peaks and troughs in the surface of the water, a peak above the regular surface, a trough below the regular surface, and this moves in the perpendicular direction away from the disturbance of the surface as the wave moves away from where the rock struck the water and moves towards the shore. We can now think of much the same as occurring for the behavior of this electric disturbance created in space. I will have a positive and negative amplitude or movement of the originally neutral field into a positive field and a negative field. So I'll be moving above and below the neutral point with a so-called amplitude or distance above to a plus field strength or below to a negative field strength for the particular wave. Now, this amplitude can vary from very small amounts to very large amounts. And how does that manifest itself in the light? The brighter the light, the bigger this amplitude would be, or the bigger the change in field from neutral 0 to high positive, back to neutral 0, down to low negative. And again, the bigger this would be, would have something to do with the brightness of the light. Notice that the amplitude varies harmonically, or meaning it doesn't grow in magnitude or amplitude, it doesn't diminish in amplitude, it stays the same amplitude if the light doesn't interact with matter. That's the key. If the light is moving through a vacuum, there's nothing to diminish this amplitude of the light, and the light will stay the same brightness as it moves through space. This is why we can see the light from stars that are unfathomably far away. There is no matter interacting with the light, so none of the electric field or magnetic field of the light is getting absorbed, so the amplitude of the light stays the same as long as it doesn't encounter matter. So the height of the peaks and the depth of the troughs will remain the same as long as there's no matter interacting. Now, notice that there's a very periodic fashion in the spacing of these heights, peaks, and troughs as well. We call that one wavelength. You can go from the height of a peak to the height of the next peak, and that would be one wavelength. You can go from the depth of a trough to the next depth of a trough, and that'll be one wavelength. No matter where on the wave you measure, as long as you measure the complete cycle of motion, it will have exactly the same wavelength. Wavelength is given the Greek symbol lambda, which is that squiggly looking letter that you see above. So that will tell you how long it takes in distance for the pattern to begin to repeat. So a wavelength has length units. It's measured typically we could use meters, but that's usually too big for light, so we will divide it up using our metric prefixes into, say, micrometers or nanometers or things of that sort, so that we can fit them on scale a little better. Now, instead of measuring the wavelength, we can also measure the so-called frequency. And what does the frequency mean? Remember, this light beam is moving through space. So if we stand at a fixed point, there will be a certain number of these waves that will pass us each second. If we count the number of waves that go by per second, that will be the frequency of the light. So you can characterize the light by measuring either its wavelength or its frequency. These are interrelated quantities, as we will see. So the frequency is typically measured in how many waves go by each second. And this is called the frequency in hertz. H-E-R-T-Z. So hertz are how many waves pass per second. And the symbol that we give to the frequency is the Greek letter nu. So we will use lambda to represent the wavelength. We will use nu to represent the wave frequency. For all forms of electromagnetic radiation, the frequency and wavelength are inherently related to one another. They must have the relationship that they are inversely proportional. Now, what does it mean to be inversely proportional? Well, quite simply, as it shows there, when one goes up, the other goes down. So if you increase the wavelength, the wave will have a lower frequency. If you increase the frequency, the wave will have a shorter wavelength. Now, this should make sense. If you want the wave's frequency to go up, you want more to pass you per second. So if the waves are shorter, more can go by per second. So as the frequency goes up, the wavelength goes down. Or conversely, if you make longer and longer waves and you stand in the same fixed point, fewer of them can go by you per second. So as the wavelength increases, the frequency decreases. Now, as a matter of fact, these are exactly inversely proportional. If you double the wavelength, you will cut the frequency in half. Only half as many can go by when they're twice as long. That's what we're saying. If you triple the frequency, the wavelength has to be 1/3 as big. If you want 3 times as many to go by you each second, they can only be 1/3 as long as they were before. So there's exact inverse proportionality between frequency and wavelength. So for any type of radiation, electromagnetic radiation, the product of its frequency and wavelength is constant. No matter what it is, if you multiply those two quantities together, you will always get the same number. So that number is one of the most important numbers in our universe. It is known as the speed of light. If you take the frequency of any form of electromagnetic radiation, multiply it by the wavelength of that same form of electromagnetic radiation, you always get the same number, no matter what type of electromagnetic radiation that is. That number is given the symbol C. Again, it's one of the most important numbers in chemistry and physics. It's known as the speed of light. It's the same value for all forms of electromagnetic radiation. Okay, so let's summarize some of the important features of this so-called speed of light. First and foremost, all forms of electromagnetic radiation travel at this same speed. It doesn't matter if it's microwaves or radio waves or television waves or visible light or any component of visible light like red, orange, yellow, blue, green. They all travel at the same speed. When you are changing from visible to microwave to whatever, all you're doing is changing either the wavelength or the frequency. But when one of those changes, the other changes proportionally. So they always multiply together so that their product is the fixed value for the speed of light. And that number, as you see in the middle of the screen, is 2.9979245 times 10 to the 8th meter per second. This is its value in a vacuum, or when there's no matter. Turns out when matter impinges on light, it slows it down a little bit. So air is really very greatly spaced matter, so it doesn't slow the light down incredibly a lot, but it does slow it down somewhat. So this number is usually written as 3 times 10 to the 8 meters per second. That is fast. As a matter of fact, this is the speed limit of the universe. Objects cannot move through the universe at a higher rate of speed than the speed of light. So this is kind of like the speed limit stuff for all objects moving around in our universe as far as we understand. Now you see what it is given there in miles per hour. It's 670 billion miles per hour would be how fast you'd have to be moving at the speed of light. So we're going to look on the next few slides at some ways in which we can use this number after we talk about the different components of the electromagnetic spectrum. Let's look at the various components of the electromagnetic spectrum. Now, all of these should be familiar to you because all of them have, maybe not all of them, but the vast majority of them have commercial uses that we employ all the time in a wide variety of applications that make our lives so much simpler and better. Remember, frequency and wavelength are interrelated to one another for electromagnetic radiation. Not all electromagnetic radiation is light. Only the stuff that we can see turns out to be what we call light. It turns out that's only a very small portion of the electromagnetic spectrum. So let's go to the long wavelength end of the electromagnetic spectrum. Just how long? Well, we'll maybe see what we mean by that in a couple example problems later. But at the long wavelength end, we will see that we have AM radio. Now, AM radio, because its wavelengths are so long, and as they fly by you, very few of them can get by you per second. So long wavelength electromagnetic radiation is low frequency electromagnetic radiation. As we now move towards the right, we're going to shorten the wavelength as we go from left to right. Correspondingly, we will be raising the frequency as we go from left to right. So again, all of these things we're showing here are made of the same stuff. They're all made of oscillating electric and magnetic fields. They're all moving at the same speed. It's just a matter of the range of how long the wavelength is, or the frequency is, determines which of these particular components you're talking about. Now, are there really sharp cutoffs between radar and infrared and between ultraviolet and X-ray? There really aren't, just one value that when you go one little tick more, you're in the next regime. These are kind of fuzzy borders for values of the electromagnetic radiation frequency or wavelength to get between the two. But nonetheless, there are well-defined regions of wavelengths, well-defined regions of frequency where we would characterize the electromagnetic wave, even though it's the same thing, by a new name when it's in that particular region of wavelength. So if we go to shorter wavelengths or higher frequencies, you will note we go from AM to FM or TV. Then from that we jump, as we continue to shorten the wavelength, we jump into what are known as microwaves. Shorten the wavelength even further, we jump to radar. Shortened even further, we come to what's known as infrared. Finally, when we get to very short wavelengths, we are now in the so-called visible range, stuff that we can see. If we continue to shorten the wavelength even further, we will reach the ultraviolet region. Even shorter, we reach the X-ray region. And then finally, when you get to extremely high frequency, extremely short wavelength light, we reach what we call the gamma ray region of light. This cartoon is attempting to show the region of the electromagnetic spectrum that corresponds to what we are able to see. Notice that we start in the gray zone there on the left with an oscillating wave-like pattern that's trying to show long wavelength. There's a long time before the pattern begins to repeat itself. As you move to the right, notice that the waves bunch up by the time you get to the gamma ray gray zone. That's trying to indicate that by the time you get there, you're of incredibly short wavelength form of light. So you notice that as we go along the electromagnetic spectrum, from the radio waves to the microwaves to the infrared, there's only a very small portion of the electromagnetic spectrum which represents the light we can see. So we have, of course, it divided up into its familiar little sections of colors, and as we see at the bottom, it says that the visible spectrum, what our built-in detectors on our head are able to look at and see, detectable with images in our mind, the light must be of wavelength between 4 times 10 to the negative 7 meters to a maximum length of the wave of 7 times 10 to the minus 7 meters. Now, since we don't like to talk in terms of those numbers on that scale, that would be 0.000004 meters to 0.000007 meters. We move it onto a scale where the numbers become a little more normal in size. So if we change to the nanometer scale, what we could say then is visible light is between 400 and 700 nanometers. For visible light, the familiar Roy G. Biv acronym states the red, orange, yellow, green, blue, violet in terms of going from long wavelength to short wavelength. So the R in Roy starts at red with long wavelength. You end with Biv with blue violet for the shorter wavelength light. What I'm showing in the picture below, though, is really going from from high frequency towards low frequency. So I'm going backwards from that. I'm going from short lambdas, again, high frequency light, to long lambdas, or low frequency light. So you'll notice that the wavelength of the short lambda end is at the 400 nanometer regime. The wavelength of the long wavelength end is at the 700 nanometer range. So I'm going from blue to red in my picture. So really I'm really going V, B, G, Y, O, R in the way that those are shown, because they're doing it in terms of increasing wavelength instead of the other way around. Okay, let's use the relationship between frequency, wavelength, and the speed of light to see if we can determine or interconvert between wavelengths and frequencies. Let's begin by looking at a so-called FM radio station. So you go onto your FM dial, and it turns out there's a radio station that says that you tune into 101.5. On the FM dial, when you tune the number, you're tuning to the frequency of the FM station in megahertz. So when you turn your dial to 101.5, you're turning the frequency of the pickup antenna to resonate the circuit at 101.5 megahertz. Now, what does the prefix mega mean? Well, we learned about that a little before. Mega means million. So 101.5 megahertz means, by converting the unit of mega, taking the metric unit away, that would be 101.5 times 10 to the 6th hertz. And a hertz is a 1 over second. It's how many happen per second. So 101.5 megahertz is equivalent to 101.5 times 10 to the 6th, 1 over seconds. So now I will use the equation for electromagnetic radiation relating the speed, wavelength, and frequency. That, of course, is C equals lambda times nu. I am asked, given the frequency of 101.5 megahertz, to find what wavelength that FM radio station is. So I will rearrange the equation and solve for lambda. That is, lambda is C over nu. So I will plug in my value of the speed of light. All electromagnetic radiation has the same value, 3 times 10 to the 8th meter per second. I don't care if it's microwaves, if it's ultraviolet, if it's infrared, or if it's a radio wave. I will use 3 times 10 to the 8 meter per second. I will now then divide that by its frequency of 101.5 times 10 to the 6th. Make sure you be careful, enter it into your calculator correctly, and when I'm done, I should calculate 2.96 meters. Now, you should put those numbers in your calculator, make sure you get that same value. So an FM radio station has a wavelength of about 3 meters. Now remember, a meter is roughly a yard. So what I'm going to tell you is that this wavelength, if you converted it to something we might know a little more familiarly, 3 meters is about 10 feet. So FM radio stations operating at this frequency have electromagnetic waves that oscillate 10 feet. Now remember what that means. It starts at 0 field, makes the maximum field, then bounces back down to 0, then makes a negative field, then goes back to 0. All that takes 10 feet of space for your FM radio station of frequency 101.5 megahertz. That's how long it takes that wave to accomplish that feat. So that might be a little surprisingly long to you. Instead of an FM radio station, let's find the wavelength of a typical AM radio station. So the AM radio station I happen to pick here is WWL. That's where you can listen to the Saints. That is 870 AM. And 870 AM means 870 kilohertz on the AM dial. So again, when you tune your radio to WWL, you turn some wizardry of some capacitor plates so that it resonates with a circuit, so that it can detect the frequency of a wave that is operating at 870 kilohertz. So if we're going to use the frequency in our equation that relates wavelength to frequency through the speed of light, we have to have the frequency exerted or expressed in hertz, not in kilohertz. So we have to know how to take the metric unit of kilohertz into hertz. 870 kilohertz, the K prefix from our study of prefixes we know means 10 to the 3 or 1,000. So 870 kilohertz is really 870,000 hertz, or 870 times 10 to the 3, 1 over seconds. So again, I will insert this into the formula C equals lambda times nu with the known speed of electromagnetic waves. I don't care if they're FM waves or AM waves, They travel at the same speed. So lambda is c over nu, and my lambda is equal to 3 times 10 to the 8 meter per second, which is the speed of light, divided into 870 times 10 to the 3 1 over seconds. Now you should notice dimensionally, the 1 over second in the numerator cancels the 1 over second in the denominator. And when those units cancel, my answer will come out in length units of meters, which wavelengths should or could be measured in. So I'm going to take my 3 times 10 to the 8th, and I'm going to divide by 870 times 10 to the 3. And if you put that correctly in your calculator, you should get a wavelength of this AM radio station of 345 meters. Okay, now that I should think is a surprisingly long wavelength to you. Let's think a little bit about what that means. 100 meters is about a football field counting the end zones. So what we're saying here is for the WWL radio frequency, each wavelength, the complete oscillation from 0 to maximum, down back to 0 to minimum, back to 0, takes 345 meters or 3.5 football fields counting the end zones. That's pretty incredibly long wavelength for a typical AM radio station. Let's this time do a frequency calculation. Instead of looking at radio waves, why don't we look at visible waves? In particular, let's look at green light. Now, to be honest with you, green light is a fairly wide band of frequencies that we could consider green. Let's consider green light that has wavelength lambda of, in particular in this case, 550 nanometers. So we would have to, of course, when we're doing the conversion between wavelength and frequency, we have to use the speed of light to do the conversion. That's more or less the conversion factor we're employing to convert frequency or wavelength, in this case, into frequency. But the conversion factor of the speed of light uses wavelength in meters and frequency in hertz. So we're going to have to take our 550 nanometer visible green light and convert it into meters. So the nano prefix, nano means billionth, so I'm going to have to take a billionth of a meter. So 550 nanometers is 550 times 10 to the minus 9 meters. Now, I could change that to 5.5 times 10 to the minus 7 meters, or I can just put it in my calculator in the form 550 times 10 to the minus 9. As long as I enter it correctly, that will be good. Okay, so again, I'm going to use the same equation. C equals lambda times nu. I don't care if I'm doing radio stations or visible light. The value of C is the same for all electromagnetic radiation. It's 3 times 10 to the 8th. So this time I'm going to rearrange the equation to solve for nu, and this time nu is equal to C over lambda. So I will put my C value in the numerator. I will put my lambda value in the denominator. Notice when I'm done, the meter units in the numerator cancel the meter units in the denominator. The dimensions I'm left with are 1 over s, and 1 over s is the physics unit that means hertz, Hz. So 1 over s is an Hz. So I will then just take my 3 times 10 to the 8th, divide by 550 times 10 to the minus 9. Make sure I put everything in the calculator correctly. And if you practice that yourself, you should come to the conclusion that the wavelength of this, the frequency of this green light of wavelength 550 nanometers would be 5.45 times 10 to the 14 hertz. Now here's what that number means. This is an incredible number. When green light strikes your eye, 545 uh, 10 to the 14 is equivalent to trillion. So 545 trillion light beams of complete cycles are hitting your eye each second. It's pretty amazing that the circuitry of your eye is able to differentiate green light from red light from blue light, because it's able to discern something striking the retina at 545 trillion waves per second striking the retina, and it can distinguish that from red, which is probably a little it's going to be a little shorter. Oh, I'm sorry. For red light with longer wavelength, it's going to be frequencies are not going to be as many waves per second there. So it's probably something, I'd say roughly 300 times 10 to the 14, roughly, or 300 trillion red light waves hit your eye per second. But somehow your eye is able to distinguish the difference between these two. Pretty incredible, really. So the relationship between energy and the components of the electromagnetic spectrum are as follows. First of all, when you have water waves and pendulum waves and swings and things of that sort, they have energy that's proportional to their amplitude, not their frequency. For electromagnetic waves, they have energy that is proportional to the frequency. The amplitude says something about how bright or intense the wave is, but the energy is packed into light waves based on the frequency. As you increase the frequency, you increase the energetic content of the wave. So the energy will increase with frequency. So if we take a look at our electromagnetic spectrum, going from low energy is the long wavelength, low frequency forms of the spectrum, such as AM radio and TV and FM. Then we go to a little higher energy of microwaves, then to radar waves, infrared, visible. Then when you get to the highest energy forms of electromagnetic radiation, the ones that are dangerous to us, we go to the high frequency forms. Those are ultraviolet, X-rays, and gamma rays. The energy packed in each bundle of light is known as a photon of energy. Let's now look at the relationship between energy, wavelength, and frequency. So of course, as we can envision, light packs energy, and when light impinges on matter, it puts energy into matter, and it turns out that the energy imparted into matter by impinging light is proportional to the frequency of the light. The higher the frequency of the light, the greater the energy content of the light. So if you, for instance, double the frequency of the electromagnetic wave, you will double the energy it carries. If you cut the frequency of the electromagnetic wave by 1/4, you will cut the energy of the light that is carrying that frequency by 1/4. Now the proportionality constant between the energy and frequency is such that is set to a value known as h, which is known as Planck's constant. So the relationship between energy and frequency is E equals h times nu, where h is a proportionality constant that connects the energy to the frequency. It turns out that it took a long time to discover this value, because the connection between frequency and energy, as you can imagine, is pretty tiny. And the proportionality constant is h equals 6.63 times 10 to the minus 34 J times S, which are joule seconds. Now, A joule is the SI unit of energy. A joule is a kilogram meter squared per second squared. So when you combine the derived units of the SI type in that fashion, you will get the SI unit of energy named after James Prescott Joule, which is a joule of energy. And so a joule of energy turns out, as we will see in some upcoming examples, it's not a huge amount of energy, but nonetheless, the amount of energy packed into light can be set equal to this magic number 6.63 times 10 to the 34 joule seconds multiplied by the frequency in 1/seconds will give you the energy of that light in joules. Now, the other thing we should recognize is because frequency and wavelength are inversely proportional through the relationship C equals lambda times nu, we can insert C equals lambda times nu into E equals h nu, and you would learn that E equals h, the same proportionality constant, times c, the speed of light, divided by lambda. What this is saying is that the energy of light is inversely proportional to the wavelength of light. So energy is inversely proportional to wavelength. Energy is directly proportional to frequency. So high frequency light is high energy light. High or long wavelength light is low energy light. And you can see that from the formula, you would be putting a big number in the denominator of hc over lambda if the wavelength of light is long. And so E will get smaller the bigger you make lambda, according to that formula. Okay, so what that says, remembering from what we have discussed earlier, that, for instance, red light is long wavelength light. Violet light is short wavelength light. Red light is low frequency light. Violet light is higher frequency light. So red light is low energy part of the electromagnetic spectrum. Violet light is high energy part of the electromagnetic spectrum. So notice again, as the wavelength increases, the energy decreases. As the wavelength decreases, the energy increases. Or in the inverse proportionality, when the frequency increases, the energy increases. When the frequency decreases, the energy decreases. Now, one more thing to mention there, if we return to our electromagnetic spectrum and we return to the various regimes of the electromagnetic spectrum, it began with radio waves, then it moved into microwaves, then it moved into radar, infrared, visible, ultraviolet, and then from ultraviolet it moved to X-rays, and then from X-rays it moved to gamma rays. This is the electromagnetic spectrum in increasing frequency. Again, radio waves, low frequency stuff, gamma rays, high frequency stuff. Well, now what we're showing here is that light energy is proportional to frequency. So the low frequency forms of the electromagnetic spectrum are low energy forms of light. Those would be radio waves, those would be microwaves, those would be radar waves, and those would be visible light waves. But then when you get to high frequency forms of light, it is high energy forms of light. Those would be ultraviolet, X-ray, and gamma rays. Now, it shouldn't be surprising to you that ultraviolet, X-ray, and gamma rays are dangerous to humans. If you get exposed to too much of these types of radiation, it can do substantial damage to the makeup of the matter of your body. Whereas we routinely have radio waves, we routinely have microwaves and radar waves and visible light waves passing through our bodies without causing any damage. Now this doesn't mean put your hand in a microwave oven, because there are certain frequencies of microwaves that stimulate motions in waters that can be dangerous. But generally speaking, if you stay away from the range where microwaves are stimulating water molecules, you're okay with the microwaves. Cell phones operate in the microwave regime, they just don't operate in the microwave regime that stimulates water molecule motions. So generally speaking, microwaves are not dangerous forms of electromagnetic waves. So in conclusion here, there's a magic proportionality constant that can tell us how the frequency of electromagnetic waves can be converted into energy. And this is a very tiny number for this proportionality constant. And as you double the frequency of light, you will double its energy. And because of the inverse relationship with wavelength, if you double the wavelength of light, you will cut the energy of the light in half. Let's look at a sample energy calculation. Let's take red light of frequency 4.3 times 10 to the 14 hertz. Seems like very high frequency light, but let's see how much energy red light of this frequency packs. Now, as a matter of fact, we did mention before that physicists state and use the word, which I'm sure you have heard at some juncture or another, that photons of light are the bundles of energy that the light carries, and the photon energy is going to be proportional to the frequency of that particular light. So what is the energy of a red light photon if it has frequency 4.3 times 10 to the 14? Well, I'm going to use the formula E equals h nu. I'm going to plug in h, and that would be a number given to you. I'm going to plug in this frequency of light of 4.3 times 10 to the 14th hertz, which are 1 over seconds. Notice dimensionally, the seconds of the proportionality constant cancels the 1 over seconds of the frequency. So when I'm done, I get E equals 2.85 times 10 to the minus 19 joules of energy. So a red light photon that turns out to be the frequency of light that plants absorb when we have green-leaved plants. We'll talk a little bit about that in our next unit of study, so maybe we'll just save that statement to be analyzed when we come to our next unit of study. Now, let's, instead of looking at a red photon of light, let's look at a UV photon of light. And let's choose ultraviolet light that has wavelength 135 nanometers. Now, I could do this problem in one of two ways. I could convert the nanometers to frequency in wavelength using the speed of light, then use the E equals h nu formula, or I can directly use the wavelength of light in the formula that represents the conversion between wavelength and energy, and that would be E equals hc over lambda, where c is the speed of light, 3 times 10 to the 8th meter per second. So that's what I do at the bottom of the slide. I take my proportionality constant h, 6.63 times 10 to the minus 34 joule seconds, multiplied by the speed of light, 3 times 10 to the 8th meter per second, and I will divide by 135 nanometers, but to make sure the dimensions work out correctly, the nanometers must be expressed in meters. So my nano prefix is 10 to the minus 9, so 135 nanometers is 135 times 10 to the minus 9 meters. If put into your calculator correctly, you should find that UV light has an energy of its photons, each photon has an energy 1.47 times 10 to the negative 18 joules of energy. Again, this is a paltry amount of energy, hardly perceptible if that photon would strike against you. Our 135 nanometer UV light photon did not possess much punch. But if you, instead of just had a single photon of that energy, let's suppose you have the SI unit of the number of things of that energy strike you, or 1 mole of photons of that energy. The mole is defined in chemistry to be the standard counting number of things, because typically numbers in chemistry are so small, like the mass or volume or even energy, as we're seeing here, are so tiny. Instead of dealing with them in individual units, we deal with them in moles of units. A mole of anything, as it says towards the middle of the slide, is an Avogadro's number of those things. It is 6.02 times 10 to the 23rd of those things. So if the UV light photon of 135 nanometers has energy 1.47 times 10 to the minus 18 joule per photon, and I have a mole of those photons, I will multiply by that conversion factor, 6.02 times 10 to the 23rd photons per mole, which will give me 890,000 joules of energy per mole when I do the conversion. Now, if I put that into kilojoules, to make that number a little more normal size, I would divide the joules by 1,000 joules per kilojoule, and that would be 890 kilojoules per mole. Now, it turns out that that is roughly the amount of energy you get burning a mole of methane or natural gas, which would be, as we show there, roughly 12, roughly, if we burn a mole of it, that's 22.4 liters of it. That's like 12 2-liter bottles of the gas, of that gas. So burning that much gas would give you the same energetic content as this mole of photons of UV light. Let's analyze the situation where we determine what the wavelength of light would be such that its photons pack energy of 1 gigajoule per mole. Okay, we say 1 capital GJ per mole. Now, a gigajoule of energy is 10 to the 9 joules of energy. So the capital G prefix means a billion. So I'm going to line up the conversion factor to convert my gigajoules into joules, and I'm going to use Avogadro's number to convert the moles of photons into individual photons. So when I take 1 gigajoule per mole, that will be equal to 1 times 10 to the 9 joules per mole, and then I will divide by Avogadro's number to get rid of the mole unit. So 1 mole is 6.02 times 10 to the 23rd photons. So the energy per photon of this light would be 1.66 times 10 to the minus 15 joules per photon. So to find out the wavelength of the light, I will stick that value for the amount of joules per photon, which it needs to be in to dimensionally work with the other units in the formula. I will use E equals hc over lambda, rearrange that equation so that it reads lambda equals hc over E, and I will plug in my h value, same Planck constant that you use in all these problems, the speed of light, same value I use in all these problems, but in the denominator I will divide by the energy in joule per photon, which is 1.66 times 10 to the minus 15 joules. So I'm going to get wavelength of each of these photons of 1.2 times 10 to the minus 10 meters. Now, if I would look at an electromagnetic spectrum, I would find that this wavelength is in the wavelength of X-rays. So X-rays pack roughly gigajoules of energy per mole, and this is enough energy certainly to do damage to tissue.